So welcome to the next recording in our chemistry review in molecular and cellular biology. And this brief recording, I want to just introduce the idea of molarity. It's a very basic concept. If you've had chemistry, it should be a very easy review. But it's really important to understand this, especially when we consider molecular biology, because it's going to be about concentrations of molecules that drive a tremendous amount of biochemistry. Right? It is a biology class, though, so I may say moles. You may think of this. That is not the mole that we're going to talk about now, though. So the mole that we're going to talk about is an Avogadro's number of something. An Avogadro's number is 6.02 times 10 to the 23rd things. So you can have a mole of bowling balls. You can have a mole of apples. We're going to be talking about moles of molecules or atoms. So therefore, 1 mole of carbon would be 6.02 times 10 to the 23rd atoms of carbon. And that happens then to correspond to the molar mass of that particular element. So the beauty of the system is that the atomic mass of carbon is 12, and therefore 12 grams of carbon is 1 mole of carbon. So if you had 12 grams of carbon measured out very, very accurately, you'd have 6.02 times 10 to the 23rd atoms approximately of carbon. Right? Now, we're not oftentimes working with pure substances. We're working with molecular compounds. And what we want is the molecular mass of that compound. So, for example, if we wanted to know the molecular weight of sodium chloride, we would take the atomic mass of sodium chloride, convert it to grams per mole. It's 22.9. Chlorine, atomic mass is 35.4 grams per mole. Where do those numbers come from? They come from the periodic table. So you need a reference until you've memorized these numbers, which the ones that you use a lot if you work in a lab, you'll have in your head. But until then, you're always going to have a periodic table or some kind of reference chart to tell you what the atomic mass is so that you can know how many grams you need to get 1 mole of that substance. But if you simply add those two together, then you have 58.3 grams per mole of sodium chloride. It makes a lot of sense. You just have to think about it a little bit. Right? Now, we need to understand what a mole is and what the molar mass is, the molecular weight of a compound is, so that we can determine its concentration in solution. We know that the biochemistry of life is aqueous-based chemistry, and therefore things have to be in solution to be reactive with each other. So their concentration then in solution is going to be very important to drive and understand that chemistry. So molarity is the most common concentration that we're going to use. You can talk about molality, you can talk about other concentrations, but molarity is really the one that you need to know well and really get a deep understanding of. You have to be able to feel it, you know what I mean? Maybe you don't, but you will eventually. And it's simply moles of solute per liter of solution. Right? So we're going to express that as a capital M, and technically it's italicized, or just moles per liter. And like I said, it's the concentration we're most commonly going to use. So you should be very familiar with that concentration. If you've had chemistry before, you have done numerous dozens, if not hundreds of problems calculating molarity or manipulating this unit. Therefore, give yourself a little test right now, and we'll work on this in class as well, but test yourself and see if you can determine the molarity of a solution that has 20 grams of sodium chloride dissolved in 500 milliliters of water. So here's the mass of your solute, and you have the volume of your solution. Now, how much magnesium sulfate would you need to make 750 milliliters of a 200 millimolar solution? Again, with a periodic table and a paper and pen, maybe a calculator if you need it, you can figure that out. And it should be relatively straightforward and easy for you to figure out. Take it to the next level. What volume of a 1.5 molar potassium permanganate solution, stock solution, would you need to add 100 millimoles of potassium permanganate? Now, this is the kind of problem that you're going to see if you ever work in a lab, if that's where you're headed, because you oftentimes make concentrated stocks that you're constantly diluting down to add the appropriate amount of the substances that you need. So if you can work through these with relative ease, you're well on your way. If you can't, crack open your chemistry book. It addresses it in most biology books. to a limited degree, but you're going to want to review this and master this concept if you want to understand molecular biology well.